Now we will come to the experimental details. Okay. Usually for electrochemistry, you can get instruments, they host both potentiostat, galvanostat and the impedance capability in one instrument. So you can get workstations. You can get potentiostat and galvanostat separately as one equipment, and what's called FRA or frequency response analyzer as another instrument, and you can couple them together and then run these experiments. Example, some of the Solartron company's products are like this. Solartron of course also sells one with the integrated facility. Normally you will get frequency ranges of 1 megahertz to 10 microhertz. Right now you can get few instruments with even higher 32 megahertz as upper limit. Above certain kilohertz, maybe 30, 50, 100 kilohertz, you do not really get useful data for normal electrochemical systems. Pure electrical systems, you can get impedance analyzers for many megahertz and gigahertz. They are not going to be useful here. They will stop at few kilohertz at the lower end. In electrochemical system, you will get benefit mainly at the middle and low frequency. Middle here meaning 10 hertz, 1 hertz, 100 hertz, in that range. Low meaning 100 millihertz, 0.1 hertz, less than that 1 millihertz. When you go to lower and lower frequency, what happens is the period is going to be inverse of the frequency. That means if I draw a sine wave, it is going to take me certain amount of time to complete one sine wave. So if I measure at 1 millihertz, I have to wait for 1000 seconds, because 1 by 0.001 is going to give me 1000 seconds. I need to apply at least one cycle. It will actually start here. Does it have a phase difference or not? If you apply more cycles, it is better, but it is going to take longer time. Usually in the electrochemical system, you can go to low frequencies to get information. It takes long time. Data tends to be noisy at low frequencies. So you want to have low frequency data, you have to wait for a long time, and still you may not be assured of a good quality data unless the system is well behaved. So if you are going to get an instrument, if you get 1 megahertz, it is good enough. If somebody says we can go up to 32 megahertz for liquid based electrochemical system, you probably do not need that. It is not going to offer any benefit. There are different types of analyzers. One is called oscilloscope. I do not think it is being used nowadays for this purpose. Okay. In the oscilloscope, at a given frequency, you will apply a potential, sinusoidal potential. You will also get current, it may have a phase difference, and you would actually plot potential and current as a function of time. It may go like this, it may go like this, and there will be a point which keeps moving in the oscilloscope. So you will trace that point, and from that you would find what is the phase, what is the magnitude. So it is I versus E or E versus I. You can get the magnitude and phase of the impedance from that. You can also see whether the response is linear. What do I mean by that? We will see a little later. But it is slow. At each frequency you have to monitor it. Maybe you can save that and take a printout and measure this value. Manually you will have to calculate the impedance. It is not used nowadays. Another type is called lock-in amplifier. It uses a technique called cross correlation. Okay. Again I will describe what that is a little later. And third is called FFT analyzer, fast Fourier transform analyzer. This term FRA is a frequency response analyzer, and most of the time it means it is an FFT analyzer, although I think sometimes it has been used for instrument which also use cross correlation. If you remember right, one of the vendors, Solartron, uses cross correlation and call that equipment as an FRA, frequency response analyzer. And of course most of the manufacturers will not even tell you how they actually analyze the data and give you this result. You click, you will get impedance, that is all they will tell. They will not show you how the current comes. I do not think many times they do not even record the current, they process it at the chip level and the chip gives you the impedance, it is saved here. You can run this in different modes. One is called potentiostatic, another is called galvanostatic. The correct term is pseudo potentiostatic, because let us say this is the potential, this is the 0 versus open circuit potential. I might superimpose 0.2 volts with respect to this, plus 0.2 volts, minus 0.2 volts, whichever, and then apply a sinusoidal wave on top of it. This is essentially saying it is more or less constant potential of 0.2 volt with few millivolts of sinusoidal potential. That is why we call it as pseudo potentiostatic. This is usually used for studying in corrosion, biosensor, deposition, most of the processes. But in storage devices like batteries or fuel cells, energy devices, usually it is a constant DC current, you might say 100 milliamps per centimeter square, on top of which we put 20 milliamp per centimeter square. Here by 20 milliamp I mean the amplitude of this. There are different ways of specifying. You can specify RMS value, you can specify the amplitude, you can specify peak to peak, means from the maximum to the minimum. Amplitude is from 0 to the maximum. RMS is going to be amplitude divided by approximately 1.4, okay, it's root mean square value. So when you choose it or when you read papers, watch this carefully. Somebody would say 5 millivolts RMS, somebody would say 20 millivolts peak to peak, somebody would write it as 10 millivolts amplitude. You will have to know how to interpret this or how to use those information. So if you want to repeat an experiment, you want to conduct at the same condition, you need to know what each of these terms mean. See, the reason we conduct in galvanostatic mode in some cases and potentiostatic mode in some cases is that the impedance values of the batteries and fuel cells are very, very low. When they are very low, when you specify potential and say 10 millivolts potential oscillation, it will give rise to large currents, okay, it may go beyond the instrument's capability. So if I give 10 millivolts potential and let us say the magnitude of the impedance is 1 milliohm, the current that I get is going to be this many volts by ohms, would give me 10 amp current. On the other hand, instrument can give a constant current or a small oscillation in the current, it can measure the potential very accurately. So here if I give 100 milliamp current, that means 0.1, I would get 10 power minus 4 voltage, that means 0.1 millivoltage at the peak. So it will actually be a sinusoidal potential with the maximum at 0.1 millivolt, it can measure it accurately. Those practical reasons which force us to use galvanostatic mode, it is not that in theory you can use potentiostatic or galvanostatic mode, there is no problem. In practice, because of the way the instrument works and because of the difficulties in achieving large current and measuring all this accurately, we use galvanostatic mode for batteries and fuel cells. When you actually run an experiment, we would expect, for example, for very simple reaction, we would expect that it has semicircle behavior, it will show up as a semicircle. But many times you will find inductive loop that comes like this in minus z imaginary versus z real. If it comes as a semicircle, I would say it is a capacitive loop. A capacitor in parallel with resistance can give rise to this. If it gives 2 loops, I would say 2 capacitive loops are present. If it comes like this, I would say it is an inductive loop, because an inductor in parallel with the resistor can give rise to this type of behavior. Now at high frequencies, you normally should not have anything except a constant value here, but you may get inductive loop, and that may not be coming because of anything in the system, it may come because of the cables. If you have long cables running parallel, what the instrument measures is what is coming to the instrument. It may come, an artifact may come because 2 cables are having an inductance, it does not know it is not coming from the cell. So you want to have short cables. Sometimes even the electronics in the instruments can give you an artifact, that means it is not having an inductance, but it gives you a measurement as if it is coming from an inductance. Sometimes in actual electrode itself, if I have an electrode like this is insulated, this is exposed to solution, the current that comes, if the distribution is not uniform, you may have this problem. If the reference electrode is placed at one end of this, for example, and the electrode is large here, the working electrode is large, I have a reference electrode, instead of I want to bring it close, I bring it to this level, because of the cell geometry I may be forced to do this. The current distribution here is not going to be uniform, potential distribution may not be uniform. This can also give rise to inductive loop. It does not mean you have a real electrochemical process, or it does not mean you have a magnetism in the system. Easy way to avoid this is to start taking data at 30 kilohertz or lower values, because you do not expect to see anything about the reaction at these kilohertz. Use short cables. Usually the kinetic and mass transfer effect will show up at the mid and low frequencies. If you have doubt about the results, what you should do is first take a dummy cell meaning it has a simple electrical circuit. These are actually resistors, physically maybe 100 ohm, 1000 ohms. You can get them from the manufacturers themselves, the instrument manufacturers themselves. Run this and see whether you are getting what you are expecting to get there. If that works, next go to system where this is called potassium ferrocyanide and ferricyanide. Many times it is referred to as Fe2 plus and Fe3 plus. Basically has Fe surrounded by and then 2 more of course. So, if you visualize it surrounded in 3D in all directions by the cyanide, and when it takes one electron or gives up an electron, these do not get reoriented. This is a large molecule. Water hydration sheath is also not that important here. So, it can take an electron or give an electron without much problem, without any reorientation. So, it is called simple electron transfer reaction. On the other hand, although we write other reactions, for example, we can write Zn plus 2 electron becomes Zn metal. Zn2 plus will have hydration sheath, that water has to go away before electron comes, and it may not even happen in one shot, it may not happen, 2 electrons will come at one shot and become metal. One electron may come, after some time it is at this level is Zn plus, and then another electron comes. So, it is not necessarily going to be a very simple reaction. So, if I want to study a simple reaction, to make sure I understand this correctly, my reference electrode is good, my cell geometry is good, usually we would take platinum or gold electrode and conduct this reaction and see whether the impedance comes as expected. If it comes as expected, then we have confidence that the equipment is behaving correctly, cabling is okay, the reference electrode is probably doing fine. So, we study the actual system that we want to study. If this does not come correctly, we have to fix this instrumentation and cable before we go on to the actual experiments. You will get different choices, single sign and multi sign, sometimes called Fourier transform in the experimental setup in the software. Normally, you will start at the high frequency. If you say we want data from 10 kilohertz to 100 millihertz, you will also have to specify how many data points are needed. These are usually in log space, but different vendors or different manufacturers will have their own set of options. You will have to choose among them. Okay. You have to give the higher frequency limit and lower frequency limit. In some cases, you can choose linear scale or log scale. Usually, we will choose log scale. You can choose number of frequencies. Imagine that I have a Bode plot, 10 power 4, maybe 10 power 3, 2, 1, 0, minus 1. This is 100 millihertz, 1 hertz, 10 hertz, 100 hertz, 1000, 10,000. We want to get data points like this. We do not want to get large space data, but then it is going to take you longer time to get all the data. High frequency, it will not take that much time, low frequency it will take lot of time to measure data at each, but then if one of the data is incorrect, it misbehaves, it just jumps up here, remaining data is clean, you will probably neglect this data and then say rest of the data I am taking it as valid. Okay. You have to tell the number of frequencies per decade, or you have to tell the total number of frequencies. You want it to be reasonably large. If it is too large, it is going to take long time. If it is too small, you will have problem in interpreting the data or understanding the data or having confidence in the data. So, there is a compromise. Amplitude you have to specify depending on how the manufacturer says it is either RMS, peak to peak, or the amplitude value. In some cases you can also specify how long you have to wait. Apply sinusoidal potential and take data right away. We know that it has problem. In some cases you will have 0 wait time giving you reasonable result. Many times we have seen that it will come like this and then it will give steady periodic results. We want to be in this region and then look at the phase and magnitude of the current and then take the impedance. We do not know upfront, a priori we do not know where it is going to be. So, you will have to guess. Some manufacturer will give you a choice of how many cycles to wait, some manufacturer will give you a choice of how many seconds to wait. Many of these cases you will have to run a trial, run few trials and then look at the data and then choose this. You may have to run it 2 seconds, 4 seconds, 10 seconds and then see which between 4 seconds and 10 seconds there is no difference, 2 seconds and 4 seconds there is a significant difference, you would say I have to wait at least 4 seconds to get stable periodic result. So, a priori upfront I can't tell you this is the correct number, depends on your system. Sometimes even waiting for 1 second may be sufficient, sometimes 0 wait time may give you good enough data. 0 wait time does not necessarily mean they will do 1 cycle and then get the result at the high frequency. At the high frequency they may do more cycles. Some instruments will give you a choice of quality, data quality, they will not tell you what they really mean by that, they will not tell you how they judge, evaluate the quality and get the results, but they give you a choice. For example, in Princeton Applied Research PAR, you would get a choice of 1, 2, 3, 4 as the quality, 1 meaning poorer quality, 4 meaning the best quality. If we say best quality, my guess is one way of doing this is I would do more number of cycles and then do Fourier transform. Even if the phase value is little off, but when I do many cycles hopefully I will get a better result, that is one way. It will take longer time. Another is to do 2 cycles, do analysis of the first cycle, do analysis of the second cycle. If they do not differ by more than a percentage, 5%, 10%, some specification, then take the test good enough. If they differ, then you do one more and then compare number 2 and number 3 result, but have a cutoff beyond 4 I am not going to go, because at low frequencies it is going to take long time. You can't say it has to match within 2% from one cycle to another cycle, because if the system is poor it will never end. So, but they will not tell you, just that they give you an indication that you will get better quality data if you choose this option. It is probably using one of these. In general it will take longer time. If at the same time they can give you the better quality data, why would anybody want a poor quality data? But these are the choices that you normally get in most of the commercial software. There is another technique called multi-sign, okay, where instead of applying one sine wave you can combine multiple sine waves, apply them together. It will take you less time to get the set of data. So, it is a shorter time. It is not possible to do this with oscilloscope or with the lock-in amplifier. You can do that with FFT analysis. Some manufacturers will give you multi-sign option at high frequencies. Some manufacturer will give you multi-sign option at low frequencies. Okay. For example, CH Instruments at low frequencies, it is, at least the version we have, it is by default it is going to be only FFT. You do not have a choice of doing single sign and multi-sign. High frequencies, if you want, you can do multi-sign. In some manufacturers case they will say high frequency will have multi-sign, low frequencies you have a choice of doing multi-sign or single sign. Some instruments will give you the option of specifying the frequencies and generating the multi-sign and doing it. Other manufacturers will say apply multi-sign, you can say how many frequencies, but I will decide what are the amplitudes and phases of each of this frequency sine waves. I will add them together, apply, get the result, do whatever analysis has to be done and give you the impedance at various frequencies. So, in some cases you would get 1 to 100 one multi-sign, 100 to 10,000 another multi-sign, that is one type of choice. You can say 1 to 10,000 one multi-sign. So, variety of things are possible. but usually my personal recommendation is not to use multi-sign. But I want to go through the details and tell you why it is not a good thing. Before that, I want to show what is done in the FFT analyzer, which is commonly used analyzer. So, I want you to understand what is FFT. Okay. FFT is a Fourier transform done for discrete points of data. You may be familiar with Fourier transform. You have a function, we are looking at periodic functions only. You can have an integral to transfer it from time domain to frequency domain, but when we measure data acquisition uses what is called A to D, analog to digital. It will take data at periodic intervals. This gets the, for example, potential or current continuously, but it will record data only at regular intervals, and that data is analyzed. Okay. So, it comes with its own limitations. So, we will continue tomorrow with what is done with FFT, what are the things one should know about FFT, so that you can understand the results that you get from the instrument. Okay. We will stop here today.